Greetings. So now we will connect game theory with the online algorithms subject. So we will use game theory to derive, for two main reasons. First, to construct, let's say, good randomized algorithms, online algorithms. And second application of game theory for online algorithms is to derive lower bounds for the possible competitive ratio of randomized algorithm. So for the possible, so with competitive ratio of a randomized online algorithm. So you see, the thing is that in game theory, so the previous videos variant of matrix games, we are having two players, each of them picks some distribution and some probability distribution, and if I view this worst thing through the lenses of the second player, of the player B, so a good strategy for player B will give me a good randomized online algorithm. That will be this video. And in the next video we'll see an application like this. This is a case when we are giving a good algorithm, a good strategy, not the best one, possibly not the best one, but a good strategy for player A. Then we will be able to derive lower bounds. So how do we do this? So for an online algorithm, so for an online problem, we can, well, associate a matrix. Well, it will be an infinite matrix, that's for sure, infinite matrix. So we will have to do some sort of pre-processing before we can work with the matrix itself. So it will be an infinite matrix, and as follows. So the rows will be indexed by all the possible inputs. So rows will be indexed by all the possible inputs. And the columns are indexed. This will be strange, but it will be indexed by deterministic online algorithms. Okay, and the entry. Okay, so how should I index this? There is a matrix, right? The row is indexed by some input vector, a complete input vector, and the column is indexed by some algorithm. Okay, so what do I have? I'm running the algorithm on this input. It will have some cost, and I just divide it by the optimum value for that particular input. Yeah, so this will be the definition of our matrix on which we play a matrix game. From the previous video. So we play a matrix game on this. Now let's see this wall concept in an example. So it will be example, and of course, as usual, we will study the ski rental program. Of course, because it's easy to study the ski rental, and let B be 4, say. Now I'm doing a slight modification of the ski rental problem. There will be no non-snowy days, so we just skip those things. So it's just a modification of the problem. There are only snowy days, which means that the input is just 1 or 1 1 or 1 1 1 or whatever. I'm just doing this in order to keep the matrix easy to understand. So the matrix's rows are indexed by possible inputs, and this means that the input is either 1, or the input is 1 1, or the input is 1 1 1, or the input is 1 1 1 1, and so on. This already makes the matrix infinite, but it will be infinite on the other direction on the possible algorithms. Now remember, deterministic algorithms, if there are only snowy days, are all having this form of A, say I, which was the by on the ith snowy day. And there was also the A infinite, which just keep renting. So these were the only options we had for deterministic algorithms, because if you get a bunch of ones, a deterministic algorithm either buys at some point or it just keeps renting. If it keeps renting, then it's this algorithm. If it buys at some point, then it will be exactly this one, because it's deterministic. So if the length 7 input it will buy on the 3rd day, then it will buy on the 3rd day for each possible input, because we are now considering only inputs containing ones, which means that I will just write here the A1 and the A2 and the A3 and the A4, and I will write here the A infinite as well, and of course several are skipped for the reason of being still slightly readable. And then so I'm just writing here n instead of these inputs, right? So instead of 1 1 1 and so on, I'm just writing down the number of ones in the input. So that will be 1 2 3 4 5 and 6. Of course, there can be more days than 6. Now the thing is, inside I have to compute these ratios, so I have to divide something by the optimum, what the cost of the algorithm. So here A1 instantly, and since B is 4, A1 instantly buys. So it's advertisements, free softwares. So 4 divided by the optimum, which is 1. Okay. Now A2 will just rent for the first snowy day, and the optimum is still 1. Actually, the optimum depends only on the input, so the optimum will be constant within a row always. And A3 runs and runs and runs and runs, and this guy also runs in the first day. Now, if the season's length is 2, then A1 still spends 4 because it buys the skis on the first day, and from that point it won't spend more money, which means that here the optimum is 2, here the optimum value is 3, here is 4, here is 4 again, and here is 4 again, because the optimum is always the minimum of n and b, the minimum of the row index and 4. So from this point on, the optimum value is constant 4. So I can just fill the denominator parts, because the optimum is, for these kind of problems, it's easy to compute the optimum value. Something divided by 3, something divided by 4, something divided by 4, and so on. Okay. This is so great. There will be something which we learn from this matrix. Okay, and A1 I will just fill in the row. A1 always spends exactly 4 on every possible input. Now A2 will buy on the second day, so it's 5, because it, if the input consists of 2 snowy dates, then on the first one A2 just rents for a unit cost, and then it will buy on the second day for a cost of 4, an additional cost of 4, and 1 plus 4 is 5. But from this point, it will be constant. Great. Now for A3, it will rent on the second day and buy on the third day, so it's 6. Now A4 will just rent, and then it will buy, and so on. Now A5 just rents, and then rents, and then rents, and now it buys. A6 is just renting and renting and renting and renting for 1 day more, and then buying. And this A infinite is just 1, 2, 3, 4, 5, 6, and so on. Now it's great. What should we do with this matrix? Now first, for today I'm player B, so let's just check player B. And I'm playing a matrix game on this cost matrix. So for example, if I choose this column and I want to minimize, my enemy player A wants to maximize. So if I choose the third column, then this guy here is 1, this is also 1, now this is 2, this is 1.5, 1.5, 1.5. So the maximizing player, the row player, would choose this point. And in this case, the value of the game will be 2. If against my strategy, player A plays the optimal strategy. Coincidentally, this is exactly the competitive ratio of A3. So an optimal play, well, if the competitive ratio is bounded, of course. So optimal counter move against B, or I would say against a pure strategy of B, so pure strategy of B, it gives the worst input, which means it gives the competitive ratio of a specific algorithm. A deterministic online algorithm. And what happens is that when I design a randomized algorithm, then I just decide probability. So with probability of q1 I will run a1, the probability of q2 I will run a2, with the probability of q3 I will run a3, and so on, q4, q5, q6, and so on. I can index this by q infinite if you wish. And okay, of course I have to satisfy some sort of equations, like the sum of qj's is just 1 and each qj is at least 0. But if there are infinitely many terms, then, well, some sort of convergence criteria should be satisfied. But yeah, so for now it's just a probability distribution. And then it says that what happens is just the other player, so if I want to win in this game, then me as player 2 I want to minimize. So I have to pick a good enough Q. Now, good enough means that it's good against any choice of player A. And okay, so it's an infinite matrix and so on, but well, we can do this, why not? So the value of the game is this, by definition. Okay, so if I'm playing this game, then this is the value of the game. But according to the Loomis theorem, this is the same as the minimum value. But here I don't have to take into account all the possible p vectors, only the unit vectors, so it's just the maximum for I, choosing the ith row of CQT. Now, which is the same as taking the maximum of the rows of CQT. Okay, and what's in a row? In a row, it's just Q1 times the cost of A1 around sigma, some sigma, so it's oops, yeah, so it's Q3, so it's if I'm just writing this out, so it's Q1 times this 4 plus Q2 plus times 1 plus Q3 times 1, blah blah blah. This will be an infinite sum on the first row. So it's to make this a bit more understandable, it will be just in the first row, that is corresponding to sigma 1 in general. In this case, it will correspond to n equals 1. So it says that the first row is just Q1 times the cost of the first algorithm run on the first possible input divided by the optimum of sigma 1, plus the same thing with probability Q2, the cost of the second algorithm for the same input divided by the optimum for sigma 1, plus blah blah blah. And it's not a finite sum, so I won't end it with a finite term. But what here we have is exactly the expectation of the ratio of my algorithm, randomized algorithm, against the optimum value for that input. And so this is exactly the expected value for the cost of my randomized algorithm on sigma divided by sigma. So that's the rho for sigma. And here I say that I should take the maximum possible such value. So this is the same as the maximum for, so I'd say that let's take the worst possible input and compute the cost of the randomized algorithm on this sigma divided by the optimum value for sigma, which is exactly the same as the definition of the competitive ratio of the randomized algorithm. So it's the competitive ratio of the randomized algorithm. Defined by the probability vector q. So this means that in order to get the best possible randomized algorithm, I only have to compute the value of the game and the optimal strategy for player B. So it means that in general, the best possible randomized algorithm, randomized online algorithm, is the same thing as winning the winning strategy, the optimal strategy, mixed strategy for player B. Now this is always the case in every online algorithm, that if we construct this matrix, which is just all, well, okay, so it's not that easy to construct the matrix itself, because you have to list all the possible rows, all the possible inputs as rows, and all the possible online deterministic algorithms as columns. But if you manage to do that in some compact way, then you have a chance to design an optimal randomized algorithm. Now in this case, we have an infinite number of constraints, which is definitely too much. So we were not able to solve this particular instance only if we manage to get this to a finite size. Now here, let's just see the part below row 4. I will now try to manage to shrink the matrix into some finite, manageable size. So first, under this row, the denominator is always 4, right? So if we have at least 4 days, then the optimum value is 4, because b equals 4 in this setting. Second, if we are moving downwards, then we are running the same algorithm, and of course the cost of the algorithm won't decrease, because if it already paid 5 in this case, then in the next day it won't spend less in total. So the accumulated cost is monotonically increasing, which means that this row is smaller than or equal to that row, and which is smaller than or equal to this row, and so on. So what we now learned for this particular matrix is that from row 4, the rows are, so they are just coordinate wise larger and larger and larger. Now remember, player A wants to maximize. Now the thing is, you cannot just cancel out all the rows, because we have that strategy of, if this row is smaller than or equal to that row, then player A won't choose this row, but it will choose that row. But since this is also majorated, so this guy is also larger, player A won't choose this row, but it will choose that row, and so on. But well, you cannot really cancel out all the rows, because it just keeps getting better and better and better. So if instead these things would be just monotonically decreasing, then it would be a valid move to cancel out all the rows but the very first one. But now it's not equivalent to cancel out all the rows, of course, because you have to retain something, and that is a theorem for linear algebra. So there is also a useful theorem from linear algebra, and it says that if u is a vector u1, the first vector is smaller than or equal to u2 and is smaller than or equal to u3 and so on, okay, and we have a system of and these guys are non-negatives, and of course here we have only non-negative numbers, because all the numbers occurring in this matrix is at least 1, and we have a system of equations. u1 times x is, say, smaller than or equal to some value t, and u2 of times x, say transposed, is smaller than or equal to the same value t, and so on. So if I have this for each possible ui, xt is also smaller than or equal to t, which is exactly the same what I get when I transform this problem into an optimization problem. Then I can replace, and here of course x is played by q right now, and u is just a row of the coordinate matrix. Then I can replace this whole system of equations by the supremum of the ui's times x transposed being smaller than or equal to t. This is the same thing. Now, what is a supremum is, in this case, it's just a least upper bound. In this case, we just have to take the max coordinate wise. Coordinate wise max. Or supremum if a maximum doesn't exist, but in this case the maximum exists. So what does it tell us now? So right now we have this row. This row is smaller than or equal to that row on each coordinate, which is smaller than or equal to that row on each coordinate, and so on. And because of this previous linear algebra formalism, we can just replace all these rows by their supremum. So from each column, from that point on, I just have to write down the largest possible value, and that's all I have to retain. Which means in this particular case that the first part of the matrix will be the same. So if I just transform it this way, I'm just writing down the last row first. So for the fourth row, 3, 2, and 1. Okay. So for the fourth row, the maximum of these values is just 4 over 4. Yeah. The maximum of these values downwards to infinite is of course 5/4. The maximum of these values is of course 6/4. Maximum of these values will be 7/4, and so on. The denominator is always 4 in each cell, and in the column corresponding to some algorithm will converge to a number which is just achieved on the day on which I decide eventually to buy the keys. So there will be these guys, and on the last column there is no maximum, so it will be just infinite, because the keep ranting algorithm will just keep ranting and ranting and ranting, and there I can use this symbol infinite. Yeah, that's great. But now I only have 4 rows instead of the infinitely many, because if I have rows in a matrix game which are just increasing and increasing and increasing, then an equivalent game is what I get by just replacing all of these rows with their supremum. Actually, when we cancelled out the smaller row, if there were a smaller and a larger row, it was the same thing, because the supremum of finitely many rows in which are ordered is just the maximum of the one, so I just keep the larger. But in this case, this is a more general case, I'm replacing this infinite set of constraints with a single one, and I'm just copying the other things. So it's 4/1, 4/2, 4/3, 1/1, 5/2, 5/3, and then I will have 1/1, 2/2, 3/3, I guess 6. Yeah, so it's already okay. I'm just trying to keep track which algorithm is which, so it's A3, and then I will have the A4, which just runs 1/1, 2/2, 3/3, and then 7, and then I will have the A5, which is 1, 2, 3, and then I will have the A6, which is just 1, 2, 3, and then I will have the A infinite, which is just 1, 2, and 3. Yeah, so right now I have this matrix. The first player will have, well, it's actually not corresponding to the input 4, it's just the input at least 4. So it's a large enough input, long enough. Now then, again, I have a matrix, and now I turn my attention into the position of B. So here we see that this particular column is smaller than or equal to this guy, and it's also smaller than or equal to that guy, because this is the same, this is the same everywhere, same everywhere, and here we have this guy is the smallest, and this is larger, and this is quite large. Now, thing is, since B is a player who wants to minimize, this means that this whole stuff can be replaced by this guy, because there is no sane option, no sane algorithm which would choose these columns, because this column is definitely better than all the other ones following this, which means that B can cancel out all these rows, all these columns. And now we are almost ready, because we have a finite matrix, right? It's a 4 times 4 matrix, which means that I can now write my system of inequalities, which seems that with the probability of 4q1 plus 2q2 plus q3 plus q4, it's at most t, because now I want to minimize the maximum. So the maximum is t, the maximum is larger, and I will try to minimize this t. And from the second column, I will get 2 of q1s plus 5 over 2 q2 plus q3 plus q4. It's also at most t. And then for this third row, I get 4 over 3 q1 plus 5 over 3 q2 plus 6 over 3 is just 2 q3 plus q4 is also at most t. And then for the last part, I'll have q1 plus 5 over 4 q2 plus 6 over 4 q3 plus 7 over 4 q4. It's also at most t. And additionally, q should be a probability distribution, which means that q1 plus q2 plus q3 plus q4 is 1. And of course, each qi is at least 0. And I want to minimize the t. The thing is, the application of game theory, the Loomis theorem, and so on, say that if I solve this system of inequalities, so if I compute the optimal solution, then I will get an optimal randomized algorithm for the ski rental problem for the case of having b equals 4. Now, this system has I would say it's a quite surprising solution. So if you just threw this into an LP solver, then you get the optimum value of q1 equals 27 divided by 175, and q2 equals 36 over the same thing, and q3, it's 48 divided by this guy, and of course q4 will be just the remainder, so it's 64 divided by this guy, and v will be 256 divided by this guy. Okay, so this is an optimal solution for this system. You can get it if you feed it into an LP solver, so you just type it into some solver. Now, this is around 1.46. What does it tell us? It tells us that for an optimal, so this solution means that an optimal randomized algorithm for the ski rental problem, if the price of the ski is 4, is that on the first snowy day we will buy with this probability, and with this probability I will buy on the second snowy day if there are at least 2 snowy days. On the third snowy day I will buy with this probability. On the fourth I will buy with this probability. Now the sum of these 4 probabilities is exactly 1. You can check it. So this means that this behavior it seems to be somewhat arbitrary, but the numbers say that this is an optimal solution for this system, which means that in expectation for every possible input, the expected ratio between the algorithm's cost divided by the optimal cost will be something which is smaller than 1.5. Now, if you compare it for b equals 4, the best possible deterministic algorithm was 2 minus 1 over b, which is, if b equals 4, it's just 1.75. So it means that for deterministic algorithms, this is the best possible bound, and for randomized algorithms this is the best possible bound. So randomization helps if we just want to minimize the expected competitive ratio. So this is how we, well, I'm not saying that we can do this in every possible setting. So for any possible problems, we are usually not that we are usually not in the situation of being able to formulate the problem and list all the possible inputs and all the possible algorithms and optimize the matrix and get a finite one. But if we can, then we just have to arrange all the possible competitive ratios like this. So columns algorithms and rows with inputs, and entries are the competitive ratios of that algorithm for that input for deterministic algorithms. And then I'll just try to, well, shrink the matrix a little bit. For example, using this linear algebra theorem, which just means that if there is a row with an ever increasing part, then I just replace this set of rows, the whole set of rows, with the limit, with the point to which they converge. And by this smart move we have only 4 rows right now instead of infinitely many. And then I'm just cancelling out all the 2 large rows, because the other player B, which is the algorithm designer, the other guy A is the input designer. And right now I was able to cancel another infinitely many rows, and I ended up with a finite matrix. And if we end up with a finite matrix, then using the usual LP formalism, we are always able to create an optimal randomized algorithm. Now, usually we are not able to do this. We are able just to filter out some rows, some columns that I don't want to deal with these and these and these algorithms. And for that algorithms, we are usually able to compute an optimal randomized mix of those algorithms. But now in this situation, we were able to enumerate all the algorithms and make an optimization of all of them. Usually we are just dealing here with a finitely many columns in the very beginning if we want to design good enough algorithm, and then we will get an optimal weight distribution for those algorithms. Now, so that was for today, and next time we will see the other application of matrix theory in which we will get lower bounds for these for the best possible randomized online algorithm. Till then, bye bye.